Recording. Okay, and there I go. Okay, so it's a great pleasure to have Yunquin Zheng from Carver Institute for Theoretical Science at UCAS, and he'll talk about continuous non-invertible symmetry. So please take it away. Thank you.
Yeah, thank you. Thank you, Sakura. Thank you, the organizers, for inviting me to speak and presenting our work. So today I'm going to explain our recent work on continuous non-invertible symmetries. And this talk is based on a work in collaboration with two fantastic collaborators, Diego de Mastro and Adar Sharon. Yeah, they're here. And okay, so let me get started. So, uh, so now we know that the idea of treating the global symmetries and topological operators on the equal footing is a very nice idea and has been very fruitful in recent years. And in particular, the most tractable case is when the global symmetry is discrete. And part of the reason is that the underlying mathematical framework for the discrete global symmetries or discrete topological operators is like more well established. Basically, they are classified by finite diffusion categories, at least in the case physicists are interested in. And then we should ask, what about the continuous symmetries? So if we follow the general idea, then we should put the continuous global symmetries and continuous topological operators also on the equal footing. And in particular, we should consider what's so-called the continuous non-invertible symmetry. They go beyond the ordinary continuous group. And the underlying mathematical framework should be classified, if we like generalize naively, this should be classified by the non-finite fusion categories or continuous fusion categories. As far as we know, this is a subject that is still under development. Okay, although there's like a systematic understanding of this type of continuous generalized symmetry is still not available yet. But there are still many examples in the physics literature, and the most well-known example is so-called cosine symmetries, which we'll discuss later in the talk. Okay, and when we learned about the continuous global symmetries, the ordinary continuous global symmetries, we all learned about the Noether's theorem. This is a very useful theorem. This tells us that a continuous invertible global symmetry G is associated with the conserved current. And this is a local current satisfying the conservation equation, D star J equal to 0. And this conservation equation is responsible for this operator to be topological. Then we need to ask, is there a version of the Noether theorem for the continuous non-invertible symmetries? And the answer is, of course, yes. And this is the upshot of, like, this is what this talk is going to explain. And the answer is yes. And in particular, the continuous non-invertible topological operator it comes is associated with non-local conserved current. I will explain what do I mean by the non-local conserved current. Okay, but this is the upshot. And we'll call this like correspondence as the generalized Noether theorem. And this generalized Noether theorem is very important. One application is that we can use this to help us to find this continuous non-invertible symmetry, because continuous family of topological operators, especially non-invertible topological operator, are generically difficult to find, but the conserved current, the conserved local operator, like the current, even if it's attached with a topological operator, is relatively easier to find. And we'll find many, many examples, especially in two-dimensional CFTs. I have to say that we are not the first to discuss this generalized Noether theorem. And this generalized Noether theorem was already known in earlier literatures. For example, in this one by Rang and Yifan from 2021, where they discussed this generalized nodal theorem in the context of the C equals to 1 CFTs. And our work is also heavily inspired by this very nice talk by Shuhen Shao in Simon Center, also from 2021, where he gave a talk, a very short talk, of exactly the same title as this talk on continuous non-invertible symmetries, where he is explaining some working progress with Sahang and Yifan at the time. And at the end of the talk, he mentioned two open questions. And what we did in our paper is to follow their idea and answer these two open questions and provide a few more examples. Yeah. So this is the outline of the talk. I'm going to explain first the cosine symmetry, which is one of the simplest example of the continuous non-invertible symmetry in detail, and then explain a little bit about the generalized nodal theorem and sketch the proof of it, and then provide a couple of examples and explain how we can use the generalized nodal theorem to find the continuous non-invertible symmetries. And I'll end by providing a summary and some open questions. Okay. If there are any questions, please feel free to stop me. Okay, so let me start by explaining the cosine symmetry. Now, let's start by considering the 1 plus 1D quantum field theory. Let's call it T with an O2 symmetry. And this O2 symmetry contains a U1 part and a charge conjugation part. The charge conjugation does not commute with the U1. It flips the charge of the U1, as the name suggests. And a representative of such a quantum field theory we should keep in mind is the C equals to 1 compact boson on a circle branch. So let's denote the topological operator of this U1 as the U of alpha, where alpha is a circle-valued number, like from 0 to 2 pi. And the topological operator associated with the charge conjugation as the eta. And in the case of the compact boson example, this operator's transform acts on the compact boson in the following way. The U1 shifts the compact boson by a phase. So we take this U1 to be the U1 momentum symmetry of the compact boson. And the charge conjugation flips the sign of the compact boson. And they obey this very simple algebra. In particular, when you cross this U1 generator by this charge conjugation generator, then the parameter associated with the U1 generator will be flipped. And another nice way to understand this non-commutativity between the U1 and the charge conjugation is that we can consider the current associated with the U1 symmetry. And the current is odd under the charge conjugation. Namely, the current is an order parameter with respect to the charge conjugation symmetry. And this will be important later in the talk. Now, we haven't reached, so these are all simple symmetries. Now, the interesting symmetry comes from gauging. If we gauge the charge conjugation symmetry of the theory that we are considering, then we obtain a new theory. And in the case of the compact boson, when T is a compact boson on a circle branch, if we gauge the charge conjugation, we'll get the C equals 1 CFT on an orbifold branch. Now let's ask, what are the symmetries of the theory after gauging? So first of all, there is a new Z2 symmetry just because we gauge the charge conjugation, and there is a quantum symmetry or dual symmetry from gauging. And let's denote the generator of this new symmetry as eta hat. Now, how about the U1 part? So what is the fate of this U1 symmetry after gauging? Since U1 does not commute with the charge conjugation, if we only look for the unitary operator that survives under gauging or survives under this charge conjugation, then only the Z2 subgroup of the U1 will survive, right? Because the only Z2 subgroup commute is the U1, the Z2 charge conjugation. So naively, one would say that like you start from a theory with O2 symmetry and you gauge charge conjugation. In the gauged theory, you will only get the Z2 times Z2 symmetry, where one of the Z2 comes from this quantum Z2 symmetry, and the other Z2 is the Z2 normal subgroup of the U1. But now we are used to the idea that we should look for not only the unitary operator as the symmetry operator, but also the non-unitary operator. And in particular, this combination is a good candidate. Why so? Because this combination is invariant under the charge conjugation transformation. Remember that charge conjugation flips like swaps the two like U1 generators. So if we take the sum of them, and they are invariant under the charge conjugation, so we expect it to survive under gauging. And this operator, like the linear combination, is no longer a unitary operator, and it satisfies, if you consider the multiplication rule or the fusion rule, they satisfy the non-invertible fusion rule. And I'm highlighting these two like relations. So what the first one implies that this operator is a non-invertible, and the second one like is just a simple property of this symmetry. It's odd. So this operator depends on a parameter alpha, and it's an even function of alpha. And because this n, this new operator, it takes the form of the cosine function of certain charge. So we call it, people usually call these two symmetry operator generates a cosine symmetry. So this is a continuous non-invertible symmetry. So in summary, so you start from a theory with the O2 symmetry, and if you gauge the charge conjugation, you will get a non-invertible cosine symmetry. Okay. Now there is a problem, a little issue, a small issue about this operator, like written in this particular form. This is because this operator, as like it's written here, is only invariant under the global charge conjugation transformation, but not the gauge charge conjugation transformation, not the local charge conjugation transformation. So, so it's not very good. And this issue was first pointed out, as far as we know, by Theo Jacobson from last year, and he resolved this puzzle in detail on the lattice. And also the same question, like the same puzzle was written in this paper, and they resolved this puzzle in the continuum contest. And we'll follow the idea in this paper in the following. And another issue about this construction, this naive construction, is that this construction makes the existence of certain conserved current obscure. It's not entirely obvious, like how do we extract this conserved current from this operator? Both issues were resolved by an alternative construction, which we learned from this paper, and this is called a sandwich construction. So the idea is very simple. So you start with the theory T, and you gauge the charge conjugation and get a new theory. So these two theories, because they are related by certain gauging, so if we put them side by side, they should be separated by a gauging interface. In particular, this gauging interface is topological interface. So we can move it like arbitrarily. We can deform its shape.
Yunqin, can I ask a question?
And yeah.
Can you explain a little bit what do you mean by the fact that an alpha is not invariant under gauge Z2 transformation?
Yeah, so we want to, like, by gauge the Z2 charge conjugation transformation, I mean, we should, because the charge conjugation is gauged, so we want this operator to be invariant under like local charge conjugation transformation. right? So the gauge transformation is like a local thing. And this operator obviously is not invariant on the local charge conjugation transformation because, yeah, that is, which is obvious, right, from this construction.
No, it's not obvious to me. Yes, isn't so if it's invariant, then
Yeah,
probably
this operator is like it is the I should really write something here. So this operator u of alpha is the exponential of e to the I alpha integration of j, right?
Yeah. Yes.
And performing a local charge conjugation transformation means that we should flip the sign of the alpha. So we should first, we should flip the sign of j for a certain point, not for the whole line.
No, but Z2 is a discrete symmetry, so you cannot
No,
just
so yeah, this is
arbitrary.
so yeah. What I have in mind is the lattice construction. So you you formulate this
I
operator
see.
on a lattice, and you flip the sign of this this local current on each link, for example.
I see.
And then this will mess up the operator.
I see. So maybe the statement is that this operator makes sense in the continuum but doesn't make sense on the lattice.
I think it also does not quite make sense in the continuum because you can always take the continuum limit of the lattice.
But I think that in the continuum, gauge transformations for discrete symmetries are not supposed to change arbitrarily point by point.
Yeah. Yeah, maybe we
Okay, it's a
can
minor point.
discuss
Okay, yeah, we
later.
can discuss later. Thank you.
Yeah, but anyway, so this
Hi, Yunqin.
construction, I think it's better. Yeah.
Can I ask
sure.
a question? So this N alpha described by the sandwich construction, how do you know that it's a simple object after this gauge? How do you know it's not decomposable?
Yeah, so yes, it's so in this particular case, it's simple. But in general, it's not. And in particular, when this K, so yeah, maybe I'll mention it later. Yeah, so in particular, when you generalize it to like these more general coset symmetries, and when this K leaves a certain G element invariant, then if you gauge this K, you will get a non-simple operator. But in general, yeah, I agree that you should worry about whether it's a simple or non-simple operator. But in here, in this particular cosine symmetry example, it's a simple operator.
Can we just be sure by like looking at the orbit, as you mentioned, that if it's a orbit which is the dimension of the group that you're gauging, then it's guaranteed
That's
to be
right.
simple.
That's right. If there's no fixed point, if there's no fixed point of this the charge conjugation transformation on this G element, then I think it's a simple. Yeah.
I see. Thanks.
Excuse me, Yunqin.
Mm.
Follow up. I just want to make sure. So can I see the N alpha under this continuum form, the gauge Z2C transformation? What does it transform to? If this is U1, then you have alpha of X local dependence, and then you make alpha arbitrary in terms of U1 gauge. In terms of a Z2C gauge, how would you express that? So maybe that will clarify.
Yeah. That's right. That's right. You should, more properly, we should promote this alpha to be a local, like coordinate dependent, and this is what this paper explained. And then you should sum over the local orbit of the alpha.
But there are some constraint in terms of the alpha, in terms of alpha of X, is it? Or
yeah. So you should promote this first alpha as a function of the coordinate and the sum over this orbit of alpha, like point by point.
Right, and that transformation will be different from U1 gauge, which will be make alpha of X.
Yeah.
There are different, maybe different global constraint or something.
Yeah.
Thank you.
Okay. Yeah, so a more appropriate construction is like this. So we first so because the two theories are related by gauging, so they are separated by a gauging interface. And if we want to ask, like, what is the fate of this U1 symmetry in theory T after gauging? So a naive way is just to sandwich this operator by a pair of the gauging interface and treat the whole thing as one object, like one defect. And indeed, we see that this construction will reproduce many of the the properties that we mentioned earlier. For instance, these two properties, which I'll explain later in the next slide. Yeah. So first, let me explain this property. So we start with this operator defined as the sandwich construction, and we insert an identity operator, which we split into a pair of the charge conjugation operator. Yeah. So on one hand, we can just like annihilate the pair and recover the original definition. On the other hand, we can also topologically move, for instance, the left part of the defect toward the left gauging interface, and the gauging interface will absorb the charge conjugation defect. And we can also move the right part of the charge conjugation defect across the U1 defect, and they will flip the parameter alpha to minus alpha, and further move it toward the right will be absorbed by the gauging interface. So so the right-hand side is nothing but this composite operator, but with the parameter minus alpha, because here we have the minus alpha. So this proves this simple property that this operator is an even function of the parameter. We can similarly work out the property, this non-invertible fusion rule in using this diagrammatic way, diagrammatic definition. Namely, when we want to compute the fusion rule of these two operators, then we put them side by side. And then we can because everything here is topological, so we can freely move, for instance, the middle two gauging interfaces together. And if we fuse them up, then you will get a condensation defect within the theory T. And this condensation defect in this particular case is just 1 plus the charge conjugation defect. So there are two channels, the identity channel. For the identity channel, we can just fuse these two U1 defect together, and you will give us this alpha plus beta. And if we are in this eta channel, then we can move this eta across this U beta, which will flip the sign of the beta, and you will get another defect, but with beta, like the parameter is alpha minus beta. So you see that this like even we haven't rigorously defined by writing a formula for this topological operator, but just drawing a diagram. But we already can use this diagram to compute many things. For instance, the fusion rule. And in particular, this fusion rule tells us that this operator is indeed a non-invertible operator. Now, having shown that after gauging we get a non-invertible operator, then we should further ask like what happens for the conserved current? Well, yes, indeed, there is a conserved current, but the current is actually non-local. So how do you see that? So we used a similar construction. So we first, so again, so in order to ask what's the fate of this conserved current for the U1 after gauging, so we just sandwiched by this current by these two gauging interfaces. And because this gauging interface is topological, so we can freely move it toward the left. and eventually hit this this local operator. But remember that this local operator is an order parameter with respect to the charge conjugation, and this interface is a gauging interface of the charge conjugation, just like the Kreimas-Wannier duality interface. So moving this interface across this order parameter will give you the disorder parameter, and disorder parameter will be attached to a quantum line, which we define as the eta hat. Okay, then we can further move move these two gauging interfaces together, and it will give you a condensation operator, or 1 plus eta hat. So you see that before gauging, you will have a local operator, and after gauging, you will have a non-local conserved current, which is attached to some topological line eta hat. And this eta hat is further attached to some non-invertible line, which in this case is a non-simple line, 1 plus eta hat. Okay. Now, as we see, so that this construction is quite general, and more generally, we can start from a quantum field theory T with a continuous symmetry G times K. And let's let this K to be the automorphism of G, and let's assume that there is no fixed point. Otherwise, there is an issue which is expected by a proof earlier in the talk. And now, if we gauge the charge, if we gauge K, then we'll get a new theory, T mod K. And in this new theory, the original G times, like G semi-cross K symmetry will become a non-invertible symmetry. This continuous G symmetry will become non-invertible. And in this paper, they call this non-invertible symmetry the non-invertible coset symmetry. And moreover, you can also see by using the same construction, the sandwich construction, that in this gauged theory, there's also a non-local conserved current that comes from this G current. And this G current, like this current is attached to some topological line eta, where this eta is the line in the rep of K fusion category. Okay. And this construction is also not limited to 1 plus 1D, and can be applied to higher dimensions as well. Okay. Now, so far, we have reviewed a very nice way of constructing the continuous non-invertible symmetry, namely using gauging. And there are two obvious questions. One was already mentioned at the end of the Schuchen's talk earlier, which is that are there new examples beyond the gauging construction? And another question is that within the gauging construction, we see that the non-local conserved current comes along with the continuous non-invertible symmetry. So therefore, we want to ask whether there is a more deeper relation between them. Do they always come along? And or this is basically the question of whether there is a generalized nodal theorem. Okay. So this is the simple construction, the gauging construction. So this brings us to explain more about this generalized nodal theorem, which is the next part of the talk. To be honest, we have not demonstrated, or we cannot prove this generalized nodal theorem for general quantum field theories. And so far, our proof only works for 2D CFTs. I'll point out in which step we use this particular effect. But anyway, let's, yes.
So can K, is there a way to generalize to the case where K is continuous also? K
is continuous. Yeah, that's a good question. Yeah, I think so. K can also be continuous, but the gauging a continuous symmetry, you mean flat gauging, right? Not the dynamical gauging.
Yeah.
Yeah, I think gauging, yeah, flat gauging also works. Yeah,
Thanks.
but I haven't seen any paper trying that. Actually, yeah, there's one point which maybe I'll mention later in one example that is related to the flat gauging of the continuous symmetry. So this K can be like flat gauging of the U1. Okay. Okay, so so this is another theorem, as I mentioned earlier, that the continuous non-invertible topological operator on alpha comes with the non-local concept of current, which we explicitly see in the case of the cosine symmetry, or more generally the coset symmetries. Now, in order to understand this generalized nodal theorem, let's understand this statement piece by piece. So let's first understand the right arrow. So let's start with the continuous topological operator on alpha. Alpha is a continuous parameter. And because it's continuous and topological operator, so there should exist a exactly marginal and spin one local operator J living on the line, where this line is responsible for triggering the change of this alpha. Okay. And because they are both exactly marginal and spin 1, so the conformal weight here is 1, 0 or 0, 1. And without loss of generality, let's focus on the 1, 0 case in this talk. Now, we have a 1, 0 operator living on the line. And then we can fold this line like this. And then we can fuse the middle part of the line. So this is just a topological move. And then we can further shrink the bubble of the line. So, and get the force figure. Okay, so this will give us some current living at the end of certain topological line L. Okay. Now, in the special case, when this N, the operator we started with, is invertible, then this L must be identity. This is because if it's like so like n times n bar, when n is invertible, must be identity. And in this case, the current we get is a local current. And indeed, this is what the ordinary nodal theorem says. Now, when this n, the operator we started with, is non-invertible, then the line L can be a non-trivial line. It can be either discrete or continuous. And for the case of a continuous case, which is what a proof expected. And I'll later mention one example, maybe. And when L is non-trivial, then we indeed get a current living at the end of some topological line L. And this is a non-local current. Okay. Okay, so this basically demonstrates the one direction of the generalized nodal theorem, namely the topological, so the existence of this topological line labeled by a continuous parameter implies that there is a non-local current. And let's look at the other direction. So in order to see the other direction, let's first review how one constructs the continuous topological operator from a continuous invertible topological operator from a local current. So let's first review the ordinary case. Well, in that case, so in order to construct this n of alpha for the invertible case, we can first deform our action by this term, like integration of the star j over some line, and we add this term into the action. This amounts to adding this term into action amounts to inserting this operator into the partition function. And this is indeed the symmetry generator that we always talk about. Okay. Now let's mimic what we do. Let me mimic this in the case of the non-invertible symmetries, the non-local current. So given a 1, 0 current living at the end of some topological line L, then we can first look for another non-invertible line B, which we call the baseline, that can have a non-trivial topological junction with L. And again, because when L is non-trivial, this B must be a non-invertible. And here we demand that these two pieces, the lower piece and upper piece, to be the same baseline, it's the same line. It's just because we want to eventually form a loop. Otherwise, we cannot form a loop of the line. And if we further take this L to be very short, we can just view this as an effective current living on this space loop. Now we can mimic the same thing that we did in the last slide. So in order to construct a topological operator, so our symmetry operator, we just first insert this baseline into the partition function and deform the action by the integration of the J, where the locus of this integration is on the base loop. Okay. So formally, we'll get this operator. And I have to point out that this expression, like a B times exponential of something, is only a formal expression. It does not mean that it's a multiplication of these two pieces. More precisely, we should define this operator by the following Taylor expansion. It's an infinite series. Yeah, we just Taylor expand this, and we just define this J in every term on this space loop. Okay. And now we define this operator, but we still have to prove that it's a topological. And actually proving this operator is topological is not quite trivial. And we spent some time in figuring out how to prove it. But ultimately, what you do is just to compute the commutator between this operator and the Ferrari generator. And we find that this commutator vanishes order by order. And therefore, this operator is topological. Now, if we are not so here, we take the advantage of the fact that we are in a CFT, so we can consider this Ferrari generator and compute the correlator. And there is some very nice technique to compute this correlator. But when the theory is not a CFT, then we do not have this expression, and compute and proving this operator to be topological is more complicated, and we don't know how to prove it for the moment. Okay. But anyway, at least in the 2D CFT case, we know that this operator is topological.
So Yunqin, can I ask,
Okay.
are you assuming here that J is an abelian current?
No, no.
But okay.
What do we mean by
There might be
abelian
other-
current?
yeah.
You mean the J can carry more indices?
Yeah, if you want that the OP of J with itself will start with 1.
Yeah, we don't assume this. So I think this proof is quite general.
But the Taylor expansion in the non-abelian case is a little bit more complicated, right?
Yeah. So we have to take care of many orderings, like path ordering and the radial ordering.
Right,
So
right.
it's more complicated, and it's in the paper.
Okay, thanks.
Yeah. Okay. And
sorry, Yunqin.
yeah.
You want to comment a little bit more about the proof. So this is n alpha coming with L n for any n for the Biot generators.
That's right.
And
That's right. Yeah.
Cancellation order by order is how does that
Yeah.
rough arrangement goes? Like maybe the second term and third term fourth term, order by order, one like a neighbor terms, some cancellation, something like that.
So each term commute with an ln. So each term,
Oh,
is topological. So
just
there's no like a miraculous cancellation.
Okay.
Yeah. So if you are interested, please look at the paper. Yeah. Right. So using here, so far we basically sketched the proof of this generalized nodal theorem, and with this we can make use of this generalized nodal theorem to help us to find new non-invertible symmetries. This is because now finding the new non-invertible symmetries, continuous non-invertible symmetry, amounts to finding the currents attached to certain topological line L. Right? And finding the currents attached, like this local operator attached to some topological line, is a much easier task, especially in two-dimensional CFTs. And later we'll see why. And moreover, if we can somehow gauge away this L to make this current to be a local current, then in this case, this continuous non-invertible symmetry is called non-intrinsically non-invertible, and which means that this non-invertible symmetry can be gauged, is gauge related to some invertible continuous symmetry, which is precisely the case that we studied earlier, like the cosine symmetries or coset symmetries. But on the other hand, when this L cannot be gauged away, then the continuous symmetry is intrinsically non-invertible. So this generalized nodal theorem gives us a way to search for these intrinsically non-invertible continuous symmetries. So with this, so I'm going to apply this generalized nodal theorem to some examples. The simplest example is, of course, the minimum model. And we need to look for 1, 0 operator in the minimum model. Here, we denote the minimum model as m, little m. This when little m is 3, it's just the Ising model. And when little m is 4, it's the tricritical Ising model, etc. Now, it's a well-known fact that in other minimum model, there's no local current, so there's no continuous symmetries. But are there non-local current, or are there non-invertible continuous symmetries? The answer turns out to be no. How to see this? First, it's easy to see this using this sandwich construction. So in the middle, so we blow up this two-dimensional minimum model into a three-dimensional slab. And in the middle is just the minimal model TQ of T. And we put the chiral boundary and the anti-chiral boundary conditions. And the chiral operator of conformal weight h, 0 amounts to considering this configuration, where a topological operator in the bulk terminates only on one boundary, especially on the chiral boundary. And the endpoint of this line in the bulk has conformal weight h. And here we want to demand that this h equals to 1. So the expression for h is like this, and we want to demand this to be 1. And we just try to solve this equation, and we find that there's no solution to this equation within this desired range. So we conclude that there's no continuous non-invertible symmetry in the minimum model, which is sort of as expected. Now the next example is the C equals to 1 CFT.
So did you also look for non-unitary minimal models?
Yes, we also look for non-unitary minimal model, and the answer is also no.
Okay.
Yeah. Good. So the next example is the C equals to 1 CFT. And because like this is the smallest central charge above the minimum models. And this is a well-known moduli space of the C equals 1 CFT. And the non-invertible symmetries are well-known also, especially thoroughly explored in this paper. And for instance, on the orbifold branch, there is a coset symmetry or cosine symmetry, which we reviewed earlier in the talk. And also on the circle branch, as well as on the orbifold branch, there are many coset symmetries, like more involved coset symmetries. And in the next slide, I'm going to rediscover them by finding the non-local current. Okay, so how to see this? Now for the moment, I'm focusing on the circle branch. So the compact boson is so I'm denoting this compact boson as phi, and it's T due as the theta. So it's well known that this theory has two U1 symmetries, the U1 momentum and U1 winding, and the topological operators are like this. We can also write down the vertex operator, which is labeled by a pair of real numbers. When these real numbers are not integers, like if they are both non-integers, if they are both integers, then this is a local operator. If one of them is a non-integer, like not an integer, then they are attached to a topological line. And they have conformal dimension like this. So in order to search for the chiral current 1,0 operator, possibly attached to a topological line, you just need to solve for the equation when dividing this h to be 1 and h bar to be 0, and solve for this equation alpha and beta. And we found two solutions for arbitrary r. So one solution is like this, where alpha is equal to 2 pi times r, and beta is 2 pi over r. And the other solution is like the inverse of the first solution. And when r equals to 1, which is the self-due radius, these topological lines are trivial, like are identity operators. And this vertex operator becomes the local vertex operator. And indeed, this is as expected because these two local operators, like 1,0 operator, together with the left current, which is the linear combination of the momentum and the winding, and together generates a SU2 current, like chiral algebra. And this is indeed as expected because the theory of the self-due radius is SU2 level 1 with the Witten model. Now, when the radius is not 1, but a rational number, when P over Q and P and Q are coprime, then these two vertex operators are non-local, but also of dimension 1,0. And there's, together with the third local current, JL, they generate this this coset symmetry, SU2, modeled by certain discrete subgroup, and which is exactly the symmetry that we constructed in the earlier part of the talk. And to see why we have this construction is because the C equals to the radius equals to P over Q CFT is related to the radius equal to 1 CFT by precisely the same gauging. Okay, so in this CFT we have the SU2 symmetry, and after gauging, because these two symmetries are not normal subgroup of the SU2, so they become non-invertible, and this is the non-invertible coset symmetry. And according to our definition, because it is related to the ordinary like invertible SU2 symmetries by gauging, so this is a non-intrinsically non-invertible. Our next example is the SU2 Witten model, and a well-known subset of the symmetry is the finity line, apart from the SU2 times SU2 symmetry, the chiral ones. And when level is k, then there are k plus 1 number of such lines. and they form these lines form the SU2 level K MTC. And then we can search for like non-local currents, 1,0 currents attached to these Ferlindi lines. Yeah. Of course, we can search for 1,0 currents attached to more general lines, but those are beyond our control. So let's, for the moment, just search for the non-local currents attached to 1,0, like non-local currents are attached to the Ferlindi lines here. Okay. And by using the same like sandwich construction, we can derive similar constraints. So we know the scaling dimension of this current, and we let this scaling dimension, like conformal weight, to be 1. And we solve this equation, and we find these solutions. So let's enumerate the first few solutions. So it means that when this level is K, 10, 18, 28, etc., the corresponding Wessel-Witten model has a continuous non-invertible symmetry. And the corresponding line that are attached to the current are these currents, are these Ferlindi lines. Now let's ask, when are these symmetries like intrinsically non-invertible? To answer this question, we need to determine when the line can be gauged away. Well, we don't know the full set of the symmetry category of this theory, so we don't know all possible ways of gauging. But if we step back and allow ourselves to consider a subset of the gauging which commute with the SU2 level K chiral algebra, then this is well understood, and this is classified by the ADE classification. And so in this case, we can determine when the continuous symmetry, like continuous non-invertible symmetry, is conditionally intrinsic. Conditional means that we need to, is intrinsic while preserving the chiral algebra. And using this ADE classification, one can tell, like one can see that only for a finite cases of Ks, this line can be gauged away, so it can be related to invertible symmetries. And this is when the case when K is 4, 10, and 28. For all the other cases, we cannot gauge away the Ferlindi line to make the current local, genuinely local. Okay, so this is possibly the first case, first examples of intrinsically non-invertible symmetries, at least the conditionally intrinsically non-invertible symmetries.
Very interesting.
Now our final, yes.
Yeah. Did you check in these cases whether the current that you have commutes or doesn't commute with the SU2 global symmetry?
The current commute with SU2 global symmetry. Yeah, we didn't check. Yeah, we didn't check. Maybe I think they generally don't commute.
Because at least in
yeah,
this
for instance, in the simplest case, if you gauge this L4, this non-local currents will become local, and they will combine with the SU2 generator to be a SU3 generator.
Yeah, okay,
so
that was
they
my
definitely don't commute.
Okay.
Yeah.
That's
Yeah.
but what about the intrinsic case, or at least the case that is suspected to be intrinsic? Because maybe in that case you don't have this nice recombination, but if you can still find some larger algebra, or maybe you cannot, this gives you an hint of whether it's really intrinsic or not.
You mean, but we cannot tell whether it's intrinsic, like indeed intrinsic, right? Because
right.
we don't know how to, like, a full set of gauging.
Yeah, right. But you can still compute the algebra formed by the SU2 chiral algebra together with additional current, and see if somehow it closes.
So this is also very this is also very annoying because so basically we want to first compute the current algebra associated with these non-local currents. But this current algebra is not closed. Namely, if you fuse the two non-local currents, you will get the operators attached to a line which are not of the dimension 1, 0. They can be like a fractional numbers, which is very confusing for us. So for the moment, we don't understand the current algebra for these non-local currents.
Okay, but that might be
But it's indeed
that might be an hint that maybe it's really an intrinsic non-invertible symmetry. Because I would expect that if it is a non-intrinsic non-invertible symmetry, then when you take the OP of one current with itself, you should get another current.
Yeah.
But okay, we can discuss this
I
later.
don't know. Yeah.
Okay.
Okay. Yeah. Our maybe the time is up, but our last example is the double the minimum model. And we can do a similar computation. But here, because we have like 2 copies of the minimum model, so there's a chance that we get a like non-local current. This is because we don't require a single line to have the endpoint of the single line to have conformal weight 1, 0, but the product of the 2 simple lines, one from each copy of the minimum model, and like the product of them, the endpoints of this product line can have a like scaling dimension 1, conformal weight 1, 0. Namely, we want the sum of this conformal weight to be 1. And indeed, there are many cases where this equation can be satisfied. And we list a few cases. And the first case is the famous coset symmetry that was already studied in the paper, in Andreas' paper, like in here. Yeah, so this is so here we find that in the double the minimum model there are many instances for the non-local currents, and the presence of this so non-local currents implied a continuous non-invertible symmetry, and this non-invertible symmetry has an interesting consequence, and the consequence is that implies that there is a defect conformal manifold for a single copy of the minimum model. This is because you can unfold this so you can unfold this thing along some boundary of this 2 copy of the minimum model, and then it means that you have a exactly marginal operator sitting on some line, and because this is not a spin 1 operator, so you integrating this exactly marginal operator will generate a conformal defect rather than the conformal defect manifold rather than the topological defect. And this construction was already known in the special case when m equals to 3 by Oshikawa and Avluk from last century. And more recently, the examples of the defect conformal manifold from this construction for the continuous coset symmetries were already explored by a very nice paper by Antinucci, Coppetti, Glatti, and Rizzi. And in the example of the minimal model is a more exotic one where the corresponding continuous symmetries are possibly intrinsically non-invertible. So it's more exotic family of the defect conformal manifold. Okay, so this is a summary of the talk. So in this talk, I explained this generalized nodal theorem, and we can use this nodal theorem to help us to find many examples of continuous non-invertible symmetries. And this is possibly beyond the gauging construction. And there are many open questions I'll just put the question here and take questions. Thank you very much.
Hey, thanks very much. It was a nice talk. Are there more questions? So maybe I will start with the higher dimensional version because of course the cosine symmetry you can study in higher dimensions, and it's more complicated because you will have to, condensation complete, and there are more things that can happen. So do you imagine these type of symmetries that you were discussing, these, whatever the terminology is, the intrinsically continuous non-invertible things to exist there or not? And these cosine symmetries are not intrinsic.
Yeah, sure.
And we studied them in Sapir, Flea, Laksha.
So first of all, the construction that we mentioned. So our this construction from the non-local current, I think only covers part of the continuous non-invertible symmetries. It's not the most general one, which we believe. This is because our construction cannot capture, as far as we understood, cannot capture the non-invertible ABJ symmetry. Yeah, if we are optimistic, we can think of the ABJ symmetry also as some continuous non-invertible symmetry, but our construction cannot capture that. So yeah, this is the first comment, that our construction is not most general. But even within our construction, and I apply our construction to higher dimensions, and when the higher dimension is high enough, like maybe 3 + 1 or higher, then I think all of the symmetries that we construct are non-intrinsic. This is because there's always a line attached to the current. And when the dimension is high enough, we can always gauge away the line to make the current local. Because the line in higher dimension is always like bosonic, so you can always gauge away. But in 2 + 1D, there may be some obstruction to gauge away the line. And in that case, there is a room for
I see, 2 + 1.
More exotic. Yeah.
Okay, thank you. Any other questions? We heard lots of questions during the talk already, so I don't see any more hands raised or anything. Okay, then let's thank Yunqin again for his nice talk. And
thank you very much.
We'll actually go back to a standard 3 o'clock GMT time next week, I believe, with Wilbur Shirley, and then one more before Christmas, which is Fabio Bruzzi, and then we break for the holidays. Okay, so thanks again, Yunqin.